For over a millennium, the smartest minds in history completely misunderstood the mechanics of human sight. This geometric breakdown illustrates the prevailing theory of the time, known as extramission. Championed by Greco-Roman thinkers like Ptolemy and Euclid, this model argued that our eyes act like lanterns, shooting out beams of light to illuminate the objects in front of us. That belief went largely unquestioned until the 11th century, when an Arab polymath named Abu Ali al-Hasan Ibn al Haytham, seen here in this engraved portrait, realized the ancient dogma contained a logical flaw. He asked a simple counter-question: if our eyes are the source of light, why does looking directly at the sun cause physical pain? That question exposed the limits of pure philosophical deduction. The Greeks relied on abstract logic, but Ibn al Haytham saw a need for a way to prove physical reality through observation. Before he could solve the mystery of sight, his life took a dangerous turn in Cairo. Tasked with building a dam to regulate the flooding of the Nile, Ibn al Haytham realized the engineering project was impossible. This failure angered the region's volatile ruler, Caliph al-Hakim. Fearing execution, the scientist feigned madness to save his own life, resulting in a permanent sentence of house arrest. His new environment was severe. Stripped of his scientific tools and books, he was confined to a dark room, the Al-Bayt al-Muslim. He now faced an incredible paradox. To rewrite the physical laws of light and vision, he would have to do it while locked inside total darkness. Sitting in confinement, he made a crucial observation. A tiny pinhole in his wall allowed a single beam of light to enter. On the opposite wall, that light projected an inverted, mirrored image of the outside world. To verify what he was seeing, he turned his cell into a laboratory, designing a series of tests to map the trajectory of individual light rays. This schematic shows the test. He placed multiple lanterns outside his dark room. Light from each traveled through a single pinhole, creating separate spots on the interior wall. Systematically blocking one lantern immediately extinguished its corresponding spot inside, while others remained intact. The physical conclusion was clear. Light acts independent of the human eye. It bounces off objects, and it always travels in straight lines. By proving that light's behavior could be accurately mapped using geometry, he turned the study of optics from a branch of philosophy into a hard science. A moment of realization. The physics of the darkened room provided a direct template for the mechanics of the human face. He formalized the intromission theory, stating that the eye emits nothing. Instead, it functions as a biological receiver for external light rays. This 11th century diagram correlates eye anatomy to the camera obscura. Geometric light rays X and Y enter the pupil, PP', acting like a pinhole. The light hits lens C, which refracts the rays, delivering an inverted image to the optic nerve N. But the physics only explained the entry of light. Ibn al Haytham realized that vision is also a cognitive process. Because the physical image arrives upside down, the brain must actively process and flip that optical data to make sense of the world. He spent years compiling his findings into a 7-volume masterwork called the Kitab al-Manazir, or the Book of Optics. 2 centuries later, the text was translated into Latin as De Aspectibus. As it circulated through Europe, it became a pillar of the Renaissance. His geometric breakdown of refraction helped Italian craftsmen develop the first eyeglasses, while his rules of projection gave Leonardo da Vinci the mathematical basis for linear perspective in art. His notes on how light refracts through lenses eventually reached 17th century astronomers, providing the optical blueprint for the first telescopes and the first detailed maps of the moon's surface. Yet the true weight of Ibn al Haytham's work lies in how he worked rather than what he found. He broke from the ancient Greek tradition of debating reality through abstract logic. To him, an idea meant nothing without repeatable physical proof. He also demanded independent verification. In his writings, he explicitly instructed his readers to construct their own dark rooms, set up their own lanterns, and test his claims for themselves. By combining hypothesis, repeatable experimentation, and mathematical proof, he didn't just teach humanity how to see. He created the protocol we now use to verify the laws of the physical world.